Hello again. Now we're going to talk about finding the limits of integration in the order dz, dy, dx. And of course, the steps in this can be reversed to change the order, but we're just going to look at this kind of conventional way of setting these integrals up and determining our bounds. So we have a 3D version of Fubini's theorem. And essentially we have the triple integral over the solid D, f of x, y, z equals maybe some function w, and then we have dz, dy, dx. So again, that's standard convention. So our first step here is going to be to sketch the 3D region D along with its shadow. And the shadow is a projection directly below into the xy plane. So this 3D figure represents D. This shadow below it in the XY plane, that's normally what we would call our R. So you'll notice here that my bounds on the x-axis, that's A and B, that's just a constant interval. My bounds on the y-axis, y is defined by two functions, y being g, a function of x, twice. So we've got g sub 1 and g sub 2. And then z, up here, we're going to find these z values. Z is a function of two variables, both x and y. So the second step will be to find the z limits. So we want to be able to determine what this z is. Z sub 1 on the bottom and z sub 2 on the top. So we have a lower and an upper bound. And what we're going to do is we're going to draw this line M directly up from a point in my surface R parallel to the z-axis. We're going to enter at my f sub 1, a function of both x and y, and we're going to exit at my f sub 2, a function of both x and y. So again, we take that point, xy in the R plane, we're going to draw up, we enter that solid at some z function of two variables, x and y, and then we continue up finding that exit, z sub 2, that function of two variables, x and y. So that gives us our z bounds, and z is again a function of both x and y. So then the next step will be to find the y limits of integration. When we look to find the y limits of integration, we come off the x-axis parallel to y along this line L to pass through x, y, that point in my region R. And we enter at g sub 1, y equals g sub 1, a function of x. we exit at y equals g sub 2, a function of x. So those give me kind of, in a sense, what we might have previously referred to as C and D. So repeating myself, we draw L. L extends out off of the x-axis. It's parallel to y, and we look at where we enter that region R. So we enter the region R at y, a function of x, and then we exit also at y, a function of x. So my z bounds were two variable functions, and my y bounds are a single variable function, y in terms of x. And then my fourth step is to find those x limits of integration, which will be constants. So we will find the least and greatest x values on that x-axis. So how do we set this up? So here we have our general setup. We integrate our function first with respect to z, and that z is coming from a bottom and a top. They are both two variable functions. And then we look at integrating with respect to y, so we get these bounds here on the y-axis, which in this case are defined by two single variable functions, y in terms of x. And then our last step is to determine those x and y bounds, a and b. So this is kind of the general setup for how we use Fubini's theorem with three variables. So now let's look at an example where we set this up and evaluate. So we have the triple integral of z integrated with respect to three variables, x, y, and z, which give us volume. And we have this tetrahedron, T, creating our solid, right? Our solid that we're trying to find the volume of is this tetrahedron. So it's bounded by three planes, x equals 0, y equals 0, and z equals 0, as well as this plane, x plus y plus z equals 0. Now these three planes are basically limiting us or putting us in our first octant. And this fourth plane, we can graph that using its intercepts. So we've got x and y and z. And if I plug in 0, 0 for y and z, that gives me the point 1 on my x-axis. I'll get the point 1 on my y-axis as well as the point 1 on my z-axis. So this is my tetrahedron. So what we're really going to focus on is going to be setting up this triple integral. All right, the integration aspect of it is going to be easy. So again, my solid here is this tetrahedron T. But what is my region R in the xy plane? And that's just going to be this triangle here. Okay, so we want to think about that region R because we may need to set that up using a function of a single variable. All right, so let's work on setting this up because again, as I said, once we've got it set up, this evaluation should be pretty simple. All right, so I'll go ahead and write my three integrals here. And we have z. So what are my bounds dz? So those need to be functions z, potentially in terms of x and y. Well, my base here, we're at z equals 0. And then my top, as we rise up through that region, we would be hitting this triangular plane. And we said that plane was defined as x plus y plus z equals 1. So can I write that in terms of z? That would be z equals 1 minus x minus y. So we've come up from 0 to touch that slanted plane. So my next set of bounds, we'll say dy. I'm going to have y equals and y equals. So here I'm going to go from y equals 0, traveling up in my region. We would touch that line. What is the equation of that line? Well, that's a line with a slope of -1 and a y-intercept of +1. So we're going to go from 0 to 1 minus x. And then my x bounds, we're going to go from 0 to 1. So we've got x equals 0, x equals 1. And then, of course, we've got our dx there. So dz, and maybe I should have written that in green to be consistent, but dz, dy, dx, z, y, x. Z can be a function of both x and y is a function of x, and then x is a constant. So it's always going to be in that kind of descending order. And the way we're defining this, and you're probably not going to see any problems where we need to do them in different orders, but there could be situations where these orders switch around and then the way we've written our functions switch around. But this is just kind of the most conventional way. All right, so now let's look at solving this integral. The algebra gets a little messy here. I'm going to go ahead and tell you it equals 1/24. If you want to pause, try and get that 1/24 on your own just to make sure you can do it, that might be a good idea. Or if you feel confident you can do it, stop watching now. What do I care? I actually care a little bit. I want you guys to pay attention, but let's work this out. All right, so here we go. Integrating z with respect to z, we get z squared over 2, or 1/2 z squared. So now we have to plug 1 minus x minus y into z, square it, divide by 2, as well as 0. Obviously, we're lucky here because plugging in 0 doesn't give us anything. But we do have some busy work to deal with. So I plug my bounds in. It looks like this. I'm going to pull my 1/2 in front. I'm going to square this, which is going to be 6 terms that I have to deal with. So once I FOIL that, I have 1 minus 2x minus 2y plus 2xy plus x squared plus y squared. That 1/2 came in front. So now we're going to integrate this with respect to y. So integrating each of those terms with respect to y, 1 becomes y, negative 2x, that's a constant, add a y. Negative 2y becomes y squared, plus 2xy, that's going to be a y squared over 2. The 2's cancel. We get xy squared. X squared is a constant, so we get x squared y. And then using our power rule to integrate, we get 1/3 y cubed. All right, so this is where it gets extra fun, right? Because now we've got to plug this function into this long drawn out expression here. So I've got y equals 1 minus x and y equals 0. 0, we're lucky all of these terms have a y, that's going to cancel out. But plugging in 1 minus x, that is some busy work algebra. So I'm just going to skip to the next step. So you can see here what that looks like when I plug 1 minus x in for each of these y terms. And we have some significant but fairly easy, busy work ahead of us to simplify. I'm going to write that next step out. So all the distribution, foiling, combining like terms, this is what we end up with. It simplifies down fairly nicely. This is easy to integrate. I have 1/2. That's going to be 1/3 x minus 1/2 x squared plus 1/3 x cubed minus 1/12 x to the 4th. And we need to evaluate that from 1 to 0. Obviously the zeros, Those are all going to cancel out, so we just need to plug 1 in. And this gives me 1/2 times the quantity 1/3 minus 1/2 plus 1/3 minus 1/12, which is 1/24. So I'm not going to give you something that's that long and drawn out on the test, but you might have to work with 3 integrals, so you need to know how to deal with this. And again, I mean, it was easy. It was just tedious because of all of this algebra here. As always, email me if you have any questions. And again, we want to remember we are really focused on being able to sketch our solid and our region, as well as setting up that integral.